Good morning class. Today we are going to discuss chiral and achiral molecule with a two stereogenic center. A molecule with a two stereo center can give rise to maximum of 4 stereoisomer, that is 2 raised to the power n, where n is number of stereo center. However, if the two stereo centers carry an identical set of substituent, the number of stereoisomer is less than 2 raised to the power n, since there will be a meso compound, for example tartaric acid. Just see, this is the formula of tartaric acid, and in a tartaric acid, just see these two carbon. These two carbon have 4 different substituent. So according to this, it should be 2 raised to the power 2, that is 4. But tartaric acid have only 3 isomers. Which 3 isomers? Just see, this is the first isomer. When we draw a mirror here, we can easily draw its mirror image. So just see, the position of this OH in this molecule is shifted on the left hand side, and this OH, position of this OH is shifted on right hand side in this molecule. So they are mirror images of each other and also have chiral carbons. That's why they are enantiomers. Now just see the third form of tartaric acid. Tartaric, in this form we clear cut see that there is a presence of plane of symmetry, and it is known as mesotartaric acid, which are optically inactive. Now just see, this is denoted by structure 1, this is structure 2, and this is structure 3. Now just see, first table is for isomer, second is for mirror image, third one is for enantiomer, and fourth one is for distereoisomers. So just see, structure 1 and structure 2 are mirror images of each other, that's why they are called as enantiomers. Now see, structure 2 and structure 3 are isomers because they have same molecular formula but different structural formula. That's why they are isomers of each other, but they are not mirror images of each other. That's why they are not called as a enantiomer, but they are distereomers of each other. Now also see structure 1 and structure 3. Both structure 1 and structure 3 have same molecular formula but different structural formula. Besides that, structure 1 and structure 3 are not mirror images of each other. So that's why they are not called as enantiomer, they are called as distereoisomers. Now we are going to see distereoisomers. Distereoisomers are defined as non-mirror images, non-identical stereoisomers. Now we are going to see properties of distereoisomers. They show similar but not identical chemical property as they contain same functional group. Rate of reactions of distereoisomer with given reagent are generally different. It is important. They have different physical properties like melting point, boiling point, density, refractive indices, specific rotation, solubility, etc. in given solvent. This point is too much important because enantiomers have same melting point and boiling point, while distereoisomers have different physical property like melting point and boiling point. They can be separated by technique like fractional crystallization, fractional distillation, and chromatography. Now we are going to see the properties of mesocompound. Mesocompound have plane of symmetry. Mesocompounds are optically inactive due to the self-cancelling stereocenter of opposite configuration. Thus, optically inactive compounds with 2 or more stereo center are termed as meso, and they possess plane of symmetry. Now we are going to discuss resolution of racemic mixture into enantiomer. The separation of racemic modification into enantiomer is called resolution. It can be done by different techniques. First technique is of mechanical separation. This method was first adopted by Pasteur for separating enantiomers of ammonium tartarate. When a racemic modification is crystallized from the solution, two types of crystals are obtained. These are mirror images of each other consisting of positive and negative form, which can be separated by hand picking with the help of pair of tweezer and powerful lens. This is very laborious method and can be applied only to those compounds which give well defined distinguishable crystal of enantiomers. Second one is biochemical method. Certain microorganisms grown in racemic mixture consume only one of the enantiomer while leaving the other unaffected. Thus, penicillium when placed in plus minus tartaric acid, that is racemic mixture of tartaric acid, consume only positive tartaric acid and leaves negative tartaric acid unused. The major disadvantage of this method is that one of the enantiomer get destroyed because it is eaten by microorganism. Third one is chemical method, which is the important method which is generally asked in the exam. This method is mostly used for resolution of racemic modification. In this method, racemic modification is treated with an optically active reagent to get pair of diastereomers. Since diastereoisomers differ in their physical property, it is possible to separate them by physical method such as fractional crystallization, fractional distillation, etc. The pure diastereoisomer are then decomposed into the mixture of optically active reagent and corresponding enantiomer, which can be separated. Just see, this is the racemic modification which contain equal amount of positive and negative form of acid or positive or negative form of optically active compound in equimolar quantity. When we add any optically active reagent, in this case we add negative base, so it means that this base also optically active. So what going to be happen? We know that acid plus base give us salt. So we got two different types of salts here, because racemic modification contain positive acid as well as negative form of acid. So we got salt of positive acid and negative base. Also we got salt of negative acid and negative base. These diastereomers can easily separable because of their difference in melting and boiling point. So it can easily separated by the method of fractional crystallization or fractional distillation. When we add H plus in this salt of acid base, what we get back? We got positive acid form, and when we treated this salt with H plus, we got negative acid. So in this case we easily separate enantiomers in pure form in this way. The commonly used active bases for the purpose of naturally occurring alkaloids such as negative leucine, negative kinosine, negative strychnine, etc. In our next class, we are going to see inversion, racemization and retention and some other concept. Thank you very much.